Hello and welcome back to Calculus 3. We are going to talk about directional derivatives and gradient in this section. Now, we already understand, hopefully, that the derivative in Calculus 1, so here, Calc 1, derivative is taken along x-axis, because we have some function, and derivative is taken along x-axis, and it computes the slope of the tangent line at point A, and we can do that at every point along, right? Then we move to Calc 3 with the partial derivatives, and we had some kind of a surface in there, and then we took partial derivatives, and that was the fx or partial f partial x. Oh no, sorry, that was f partial x. Now technically, if you are taking derivatives, partial derivatives, what you are doing is you are slicing the object. We had that picture before. That edge that it's created, which is represented with blue and red lines here on top, that edge is the actual two-dimensional function, and you just have a regular derivative. But now, this is supposed to say Calculus 3, partial derivatives. But now, I want to achieve the derivative in any direction. So not just along x-axis or along y-axis and parallel, obviously. I want at any other direction. So if I have x, y, z coordinate system, and let's say I have, again, some kind of a surface, how about the derivative in this direction? So that would give a rise to the cut. So we would have some kind of a plane that would cut through the object, and that would make a line, certain line, on the surface of the object, and now that would be the derivative. But that's not a partial derivative anymore, because this one is not going to be along x or along y or any parallel directions. This is in between. So this particular, we can call this vector u. I'm just going to switch back over here. And we will call this one vector u, because that gives us a new direction in which we want to find the derivative. So now this red line, which is on the surface of the object, will also have the tangent line at the point and so on. So maybe this point here will give rise to this point here, and then there is a tangent line that we can draw at that point, which has a slope, and slope has to come from the derivative and all of that stuff. So yeah, not easy to draw this thing, but hopefully we understand that this particular cut comes from, the plane that was built on this arbitrary, well, we usually know which direction we want to look at, so it's not arbitrary, but in this picture is arbitrary, vector u. So what do we do here, right? How do we deal with this? So directional derivative will be given to us in the direction of the vector u. And we are going to have, again, a definition for this. Looking at the picture, but also we're going to have the theorem which will give us the easy computation. So you remember that we have that duality from before, where you define it one way and you use formula to compute easier the other way. So let's talk about the definition first. Let f be differentiable at a, b, and let vector u, and guys, this is u hat, so let vector u, u1, u2, it's a vector, so spiky brackets, be a unit vector in xy plane, be an unit vector in xy plane. Then the directional derivative of f at AB in the direction of vector u is, and now we have the notation for it, d in the direction of u of f at AB. It's a little bit long notation, as you can see, but d stands for derivative, so derivative of f computed at AB, and then the lowercase u up there as in the index is in the direction of u, is given as the good old limit h goes to 0, and then we have f of a plus age u1 comma b plus age u2 divided by, so minus f of AB, come on, divided by h. There we go. So this is the limit definition of the derivative, and you see all of the features of the limit that you know from Calculus 1 are still here. You have your f of x plus h minus f of x divided by h, except now you are dealing this at the point, so it's a plus h, and then we're also, as you can see, multiplying by the vector u, because that's giving us direction. Now remember, it's a unit vector because the magnitude of a unit vector is 1. So if you are multiplying by the unit vector, you are not changing the magnitude, because the magnitude is 1, right? So your derivative will preserve its slope, its value, because you are multiplying by 1. The only thing that you are gaining from the unit vector is the new direction, right? So that's that part. And the way we use this in a formula, right? So formula that we use to actually compute this directional derivative FAB is actually going to be the dot product between partial x computed at AB, comma, partial y computed at AB, dotted with vector u, so u1, u2. Now that is what we are going to use to compute this. You clearly want to use dot product between two vectors. You are not going to crank the limit every time you have to find this.
Is that a minus over there, like the?
It's a dot for the dot product.
Okay.
Better? I guess better. right. So find directional derivative for f of xy equal x squared y minus, I don't know, minus x, whatever, at 3, -1 in direction of u equals 3, 4. Yes.
When you were writing up the formula, you said partial. So
That's what the little x and little y are
okay. So
in the notation.
okay.
The other notation is much longer. You can also write it as partial f, partial x, computed at AB. It's much longer to write it this way than partial x computed at AB. Is the same notation, different notation for the exactly same thing. We know that this vertical line means compute that, right? Just like for integrals. It's been enough time. If your formula has 3 and 4 as a vector u, you are doing it wrong. So now look at the paper. Take a look if you have 3 and 4 in your vector. And if you do, it's time to redo the problem. What is vector u? In a definition? Okay, is 3, 4 unit? No, right? Good. So, we have to figure out the unit vector and plug it there. Usually that's what kills your grade on exam 2. So make sure that the vector 2 is unit. Otherwise, it will change the value of the derivative and the answer you have at the end will be wrong. So we first find the unit vector. We check the vector u first. And in this case, clearly it's not the unit vector, so we have to deal with that first. And then we can plug everything into the formula with derivatives and figure things out. So, vector u hat is going to be 3, 4 divided by the square root of 3 squared plus 4 squared, which will be 5. So unit vector is 3/5 and 4/5. You can also keep it as a 0.6, 0.8, depending what's your favorite. So now we have our directional derivative in u hat f of 3 negative 1, which is the partial derivative of, you can find the, you know what, let's find the partial derivative first, so that we don't have to keep, I generally skip that step, I just do it as I go along, but since we are learning, let's find the partial x first. Partial x is simply 2xy minus 1. And then we find partial of y, which is just x squared. So now, we do partial x computed at a, b. That's going to be 2 times 3 times negative 1 minus 1. So that's partial x. Comma, partial y computed at this is just 3 squared. And then times 3/5, 4/5 as a dot product. So the first calculation here is negative 6, negative 7, 9, and then we have dotted with 3/5, 4/5. So this works out to be negative 21/5 plus 36/5 for the total of 15/5, which is 3 in my opinion. I don't know. Is this good? So, yes.
A quick question. When we took the derivative for y in this case, I understand why we had to take the derivative that I left with the x squared as a constant, but what happened to the other x? Did we just leave it in 0?
Yeah.
Okay.
Because when you're taking the derivative of y, all x's are treated as constants, so this might be just like x squared y minus 3, and you would put that to be 0, right? So whatever is that part is a constant. Okay, and then we plug in our point, 3 negative 1, 3 squared, that's 9, good, so negative 7, we have negative 6 minus 1, yep, so this should be good. So this is the way to compute the directional derivative. Now we can actually compute the tangent line, right? In this case, because we have everything. This is just going to be now addition to the problem, just because we can. So add, find tangent line. Remember what we have. We have now that the derivative is 3, right? So we have the slope. And we can calculate. We have the direction, we have the slope, and we have the point. And we know that in 3D space, line is given as x equals x0 plus at, y equal y0 plus bt, and z equals z0 plus bt, right? So we can calculate, we have our function z equals f of xy, which is, what was it, just x squared, right? X squared y minus x. So you can calculate z, which will give you z0, because you have the point 3, negative 1. You have a point 3, negative 1. Yes?
For z, isn't it going to be z0 plus ct? Or is it just
Oh, C, yes, you're right. Sorry. Oops. I'm not sure why I put BT. Yep, CT. It's ABC for the, yep. So x0, y0 is given, and you can calculate z0 now by simply plugging in x and y. So that's 9 times negative 1 minus 3. It's going to be negative 12. So now we have x0, y0, z0. We have the slope, we have the direction given by the vector. Just plug everything in. So we can actually find the tangent line. We are more interested in tangent planes for the 3D case. It's coming up, right? But you can find the tangent line as well along the vector 3, 4. Because remember, when I have an object and I cut that object with a plane, so I have some kind of object and I cut that object with a plane, your derivative is now two-dimensional along that cut. See? So this vector, I adjust this. There is a vector along the bottom line that it's 3, 4, right? So I draw 3, 4, and I put the plane, and that plane will cut the shape somewhere. The surface of that shape is now two-dimensional right there where the cut is, and then there is I need like 15 hands now. There is a tangent line at the point over there. I can't just hold everything, but there's that. So now that you have all of the things given, you have the point AB, so that's AB, that's x0, y0, and you can compute z0 at that point. So those are these guys, and the vector ABC is the direction between the derivative and directional vector, right? So there you go. And t is just a parameter t because the line is infinite. You leave t as t. Yay. So what are we going to do now? Now we're going to just give this piece of a vector, we're going to give it a name. It's called the gradient. The gradient vector. Delta f of xy, and that's a vector, so you have to put the vector above this triangle, and I'll explain that one, is actually partial derivative of xy, comma, partial derivative of y and xy. This is your two-dimensional gradient vector. We read this triangle as del. So, and this is read as del of f, or you can just say del f. You can read it either way. That's just the way you say it. And we're just giving it a name. That's all it is. So now we can rewrite our formula for directional derivative by simply writing del f computed at a, b, that's a vector, dotted with vector u hat. So now this is a short way, right? Short way. Short notation for directional derivatives. So now I'm going to go back and take a look at this formula. All I did here is I replaced this thing with del f and this one with u hat to make short. It's still the same formula, just make a shorter notation. It's much easier to remember these vector formulas, and these vector formulas are actually better because, right, if they don't involve cross product or something like that, they work in any dimension. So now we can talk about directional derivative in 3D, 4D, 7D, 13D, doesn't matter, because all I need to do is to have ABC, ABCD for 4D, ABCDE for 5D. Vector u will have enough components to match the amount of variables you have in a function. So it's always like that. We can also define del of f of xy as fxi plus fyj, right? We can also do that. It's okay. You can use the notation with spiky brackets, or you can use ijk. It's okay. And now, why are we dealing with this gradient? See, gradient is going to give us the measurement of a change. You see that gradient is a vector of derivatives, and we know derivatives measure the change. Therefore, the gradient is going to measure the change. And we have a theorem that puts this in perspective. And guys, this theorem is the one that you need to know, because this is how you measure the change in a three-dimensional space. So I believe it's labeled theorem 1211, but we're just going to say theorem directions of change. So theorem directions of change. Please make sure that this particular theorem is visible, because this is how you do problems, and this is how you do word problems as well. When you are looking at the object, please look at this slanted cylinder. You see that it has curvature, curvature, and it also has slope, slanted slope in different directions. Imagine an ant somewhere on this object. There is going to be, when the ant is standing right in one spot, there is going to be the steepest way down and the steepest way up at each point where the ant is. So if the ant is standing somewhere, right, the ant can go down the slope or down the curve in certain direction, and then up the slope or up the curve in certain direction. Only one direction would be the fastest way down, and only one direction would be the fastest way up, measured by the gradient. Okay? So you see how important this is. You can think about the terrain, but there you can think about many other things. Civil engineers, right? You want to construct the roads through mountains and hills and things like that, right? You don't want your road to be at the slope of 7, right? So we have to think about those things. So let f be differentiable at a, b with the gradient different than 0. We don't want gradient to be 0, right? Because then there is no change. Gradient of this surface of the desk is 0. Right? Right. No change in elevation. It's flat. So let f be differentiable at AB with del FAB different than 0. Number 1. F has its maximum rate of increase at AB, so this is happening at the point, right? Ant is standing somewhere. In the direction of the gradient, del FAB, and the rate of change in this direction is the magnitude of the vector. So the rate of change in this direction is the magnitude of the vector FAB. F has its maximum rate of decrease at AB in the direction of negative gradient FAB. The rate of change in this direction is negative absolute del FAB. Number 3, the directional derivative is 0 at any direction orthogonal So the directional derivative is 0 in any direction orthogonal to the gradient, which should make sense because the dot product, right? Gradient dot direction vector, the unit vector. So if they are orthogonal, the derivative there is 0. There's no change. So now this allows us to find the steepest ascent and the descent for a particle or a bug or whatever on the surface. And here this is page 921. It's just a quick graph where you can see a shape. This is an elliptical paraboloid. Now we have the directional derivative in the direction of the vector u, which is the blue arrow. You see a plane cut through the shape. You see a black outline, right, where the object intersects the plane of the cut. And the derivative, directional derivative, is happening along that black line. You can also see a point where the end is. And along that black line, blue line going up, that's the steepest way up. And the red line going down is the steepest way down. And that is what the gradient shows in this case. So the fastest way up and the fastest way down at any point when you are on the plane. Now, if the plane the surface is flat, then there is no fastest way up or fastest way down. Right? There's no fastest way down now that I'm standing on this. I can go through the floor, right? And there's no fastest way up either, because there is nothing for me to walk on, right? Jumping doesn't, right? Because you have to be touching the surface at all points. That there is the meaning that you are on the shape. If you jump off of the shape, you're not on the shape, obviously. So jumping doesn't count. So you have a flat surface. There is no fastest way up or fastest way down. It's just flat. But if you're on any kind of sloped surface or on a round surface, right? There is fastest way up or fastest way down, obviously. And then that's calculated by the gradient, and then the value of that slope is given simply by the magnitude of the gradient. So let's calculate one of these problems from homework. So there's something fun. Ooh, problem 31 is amazing. Your function f of xy. See, and now the function is given as the function is given as capital F. So when you are using your notation, you should have a gradient of capital F, because that's what was given there. So capital F is given as e to the negative x squared over 2 minus y squared over 2. So the entire thing is in the exponent. And the point P is negative 1, 1. Find the unit vectors that will give us the direction of steepest ascent and steepest descent. At P, find the vector that points in the direction of no change of the function. What can you tell me about the function when you look at it? Did we learn anything? What can you tell me about the function? Symmetric, thank you. So that should, if you see a symmetric function, it cuts your calculations for the partial derivatives either in half or in thirds if you are doing the 3D problem. So we calculate fx partial derivative in respect, so e, we just get to copy everything as is, and then times the derivative of the exponent, which would be negative 2x over 2, and then these 2's would cancel. So the actual derivative is negative x e to the negative x squared over 2 minus y squared over 2. That's the directional derivative. Immediately, because of the symmetry, we can write negative y e to the negative x squared over 2 minus y squared over 2. This skill is important because it cuts on calculation to notice the symmetry. Again, what is the symmetry in these equations? If you are able to swap x with y and still have the same problem. The only thing that saves this problem is this minus here. That's the reason we can swap. Remember that subtraction is not commutative. So without this minus, this would not be symmetric. With the minus it is, right? Because now by swapping x and a y, it's like swapping these spots, but each one has a minus, so it's okay. All right, perfect. So we have that. Now we can calculate from there. We can calculate del f at negative 1, 1. So that means negative x, so that's going to be negative 1. We're looking for the vector, so spiky bracket. Negative 1 e to the negative 1/2 minus 1/2. The squares will kill the negative over there. And then we have comma. Negative y is 1. And we still have negative half in the exponent. So del f at negative 1, 1 is given by the vector e to the negative 1, which is 1 over e, comma, negative 1 over e. 1/2 minus 1/2 is minus 1. E to the minus 1 is just 1 over e. So we just have 1 over e and negative 1 over e. And this is already the fastest way up. So this is the direction of the steepest ascent. Then we immediately go with the negative 1 over e, negative 1 over e, which is negative 1 over e, 1 over e, and this is direction of steepest descent. Now, please understand that these are the vectors in xy plane. So these are the vectors in the domain that would give rise to that cut that would eventually hit the function, right? Now the rate of the steepest ascent and steepest descent in this case would be the magnitude of this. So rate would be the magnitude of the gradient. Now this is a symmetric function, so they're both the same. One is positive, one is negative. We have a square root of 1 over e squared plus negative 1 over e squared, which is 2 over e. And that would be the slope. So this is the rate of descent and ascent. Obviously, ascent is positive and descent will be negative because you want your derivative going down, right? To be negative and derivative going up to be positive. So positive and negative of this. So rate is plus minus this one, plus goes with this and minus goes with that. One more part to this problem. In which direction there is no change? What is the direction for no change? Usually that is the confusing part if you don't understand what's happening here. Answering that question is tricky. So all of this was part A. And now part B. It's worded: find the vector that points in a direction of no change in the function at P. Find the vector which points in the direction of no change in the function at P. And P is given as 1, negative 1 or negative 1, negative 1, 1. So the directional derivative is 0 in any direction orthogonal to the gradient. Clearly we have to use that, right? The directional derivative is 0 in any direction orthogonal to the... So what should we do? Yes?
Can you go scroll back down? I didn't finish.
What do we do?
Do something to with the cross product and how you go back.
Okay, well we have the gradient, right? We know that the gradient of f xy, well, at the point negative 1 was given as 1 over e, negative 1 over e. The directional derivative of f in negative 1, 1 is going to be gradient of f dotted with u hat. And we want that to be 0. We have that the gradient is 1 over e, negative 1 over e. We don't know what u1 and u2 are, but we know that the dot product we want to be 0. So can we solve this equation somehow?
I'll use the 0 vector.
Well, that's a trivial solution.
So I tried.
Zero vector would definitely kill it, yeah. But 0 vector is not a unit vector, right? Does not have magnitude of 1, so we have to exclude that one. Does it make sense? So 0 vector would work, but it doesn't work with the concept, because we must have a unit vector there. A 0 vector cannot be made into a unit vector. So you're going to run stuff like this in linear algebra, yes?
Can you make U more than 2D?
Sure. You can also make them 1, 1. See, you just need to guess. You just need to guess anything that would work. So would EE work? Sure, EE would work. While also 1, 1 would work. See, the trick is that you actually, once you find U1, U2, then you have to make a unit vector out of it. So, can you use EE? Sure, but then making a unit vector out of that is going to be annoying. So, pick 1, 1. Because, well, let's put U1, U2 equals vector 1, 1. Because that would definitely satisfy this equation. You have 1 times 1 over E plus 1 times negative 1 over E. That adds to 0. Yes?
I was just asking for the direction, so why do we need to find the unit vector? It's not asking for like the rate or anything like that.
Well, see, the unit vector is only the direction. The full vector U also has a magnitude. So the magnitude of this vector is root 2. Does it make sense?
Yeah,
but the unit vector is only direction.
That line would be the...
That's true. Mm-hmm. It's just a standard thing.
Okay.
So 1, 1 does it. Look, you can just say at 45 degrees. That does it too, right? See, when you give a vector 1, 1, it gives you the direction, which is the same as the direction just saying 45 degrees, right? But it also pins the magnitude at root 2. Now, it's good to have the... I mean, I won't mark it wrong. It's just that I've seen it way too many times on the exams when students just put 3, 4, right? And then it kills. So if you get used to the fact that you are multiplying by a unit vector because you only want to add the direction, then the unit vector becomes something like simultaneous with give me the direction only, right? Because the unit vector has the magnitude of 1, and that 1 does not change the original other thing that you are working with. So that's why. But so the answer of 1, 1 works. The answer of EE works. I would say vector U is root 2 over 2, root 2 over 2. And that would be the direction. You can also answer it with, you can answer it in any way you want. I don't know, maybe my OCD is too much. You guys are going to see this type of calculation more as you go through your calculation. Eventually you will be looking for eigenvalues and eigenvectors, and they will have something similar to figure out things. So yeah, that's that. Okay, cool. All of this obviously works in 3D by adding another variable to your vectors, right? Adding z component, adding c to your point, adding extra calculation for the unit vectors as plus c squared under the root. So the whole thing just becomes a little bit longer to compute, and obviously we're getting a little bit more annoying for the calculation like this, right, where you now have to match U1, U2, U3 to make the stuff work. So gradient in R3 is going to be del f xyz with fx xyz comma fy xyz comma fz x, y, z. Calculations are identical. I'm just going to show you the problems. They're right here. So instead of taking 2 partial derivatives, now you have 3 partial derivatives computed at 3 points. Note how nice the people that write the book. They give you already unit vectors here, not so much here. So you have to come up with unit vectors. You have your point, obviously, and then unit vector. Is this unit? Yeah, it is actually. 4, 4, and 1. 4, 4, 8, and 1 is 9, and this is 3 squared is 9. Wow, they're all unit vectors here. They did that for you, so you should maybe write a thank you note and send it to the author of the book. Thank you. You don't have to do that, but please get in the habit of checking if the vector that is given to you is unit vector, because again, you need the direction only. Next lecture is on tangent plane, linear approximation, and differentials. So take a few minutes break.